Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It is our first lesson on the third topic of Form 4, which is called floating and sinking. As usual, let me commence by giving you the quote of the day, which states that kindness is a language which the deaf can hear, the blind can see, and the dumb can speak. We shall discuss that quote at the end of our class today. So today we are looking at verification of Archimedes' principle. But first of all, we need to understand where the term Archimedes is coming from. So Archimedes is originating from the name of a Greek scientist by the name Archimedes, who first carried out experiments on how to measure the force of upthrust, or how to measure the upthrust force. Remember, under force, that is in Form 1, we did define what we mean by upthrust force, whereby we said that it is an upward force that is exerted on a body which is immersed in a fluid, whereby we say that a fluid can either be a liquid or a gas. So to verify the Archimedes principle, the apparatus that we need, one, we need a spring which is calibrated in newtons, because we need to measure the amount of force or the weight. Then we also need an object. In this case, we are using a stone. We also need a string. In some cases, we can also use a thread. We also need a EUREKA can. A EUREKA can is also called an overflow can. We also need a beaker, of course, for measuring, that is the displaced water or fluid. Then you also need an electric balance to measure the weight of the displaced water. So these are the apparatus. We have our spring here. We have our stone or the object. We have our string or a thread. Then of course, this is our EUREKA can, also called an overflow can, because when the water is, or when the fluid is inserted in that particular container to a certain level, actually the excess liquid flows over. That is why it is called an overflow can, or simply a EUREKA can. So this is our beaker. Then this is our electronic balance to measure the weight of the displaced water. Then this is our bench, whereby our EUREKA can is resting on it. Then of course, we are attaching our spring somewhere within the air. So we need to look at the characteristics of the object to be used in this particular experiment. Of course, here we are using a stone. So it is not all objects that can be used in this experiment. So the object to be used, it must possess some certain characteristic. One of the characteristics is that the object to be used, it must be non-porous. Non-porous simply means that it does not have the pores, or it does not allow the fluid to flow through. In this case, the fluid, we are talking of the water. So the object should be in such a way that it does not allow the water to pass through it. The second characteristic is that it should be insoluble in that particular liquid or in that particular fluid, because suppose it was to be dissolved, then it will be very difficult to obtain an accurate amount of displaced water due to that particular object being inserted in the water. Then the third and the last characteristic is that the object to be used, it must be non-reactive with the liquid being used. Suppose the stone was reacting with water. Actually, remember, a reaction can lead to explosion. So these are the three basic characteristics that you must consider when choosing an object to be used in the verification of Archimedes' principle. Then let's look at the procedure. So the first procedure, you weigh the object in air, of course, as shown in this particular diagram. So you simply find the weight of this particular stone in air. Then of course you record it as W air, that is weight in air. Then record it as W air, and you also find the weight of this particular object when immersed in water. Then of course you record it as W water. Then the second procedure, you fill the EUREKA can or the overflow can with water and place it on a bench, that is as shown in this particular diagram. So you fill it up to the brim, so that the water, just fill it to the maximum point possible. Then you place it on a bench so that it is resting, or it is in a state of rest. Then after that, you weigh the empty beaker and record its weight as W beaker. So you find the weight of this particular beaker when it does not have any displaced water. You record its weight. Of course, the weight will be measured using an electronic balance. You record its weight as W beaker, that is weight of the beaker. Then the third, that is the fourth procedure, you immerse the object, that is this particular stone, you immerse it in the EUREKA can completely and collect the displaced water in a beaker. So of course you can see this is our displaced water as a result of immersing this particular stone in the water that was placed in a EUREKA can. Then after that, you weigh the beaker plus the displaced water and record it as W beaker plus displaced water. So again, using your electronic balance, you find the weight of the beaker plus the displaced water. Then you record it as the weight of the beaker plus the displaced water. Then under observation and conclusion, first of all, you find the upthrust, which is also called the apparent loss in weight. So earlier on, we saw that upthrust can be given by the weight in air minus the weight in water. That is the value that you found here, W, the weight of the body when it is in air, as shown in this particular diagram. Then you subtract the weight of the body when it is completely immersed in water. So you simply take the spring reading here, you subtract with the spring reading at this particular point. So upthrust, also called the apparent loss in weight, will be equal to the weight in air minus the weight when the body is immersed in the fluid. The fluid in this case is water. Then you also you find the weight of the fluid, that is the displaced fluid or the displaced water. So the weight of the displaced water will simply be given by the weight of the beaker plus displaced water. Then you subtract the weight of the beaker. Remember, W beaker plus displaced water is the weight of this particular beaker plus the weight of this displaced water. So if you take that weight, then you subtract the weight of the beaker alone, you will simply remain with the weight of the displaced water or the displaced fluid. Then after that, if you compare the value obtained here, that is W air minus W water, you compare it with the value obtained in this particular equation, that is for W beaker plus displaced water minus W beaker, you would realize that those particular values are exactly the same, or they are closer to each other. So that simply shows us that the W air minus W water, the value obtained as a result of subtracting the weight in air minus the weight in water, will be equal to the value that is obtained as a result of subtracting the weight of the beaker plus displaced water minus the weight of the beaker. So since W air minus W beaker is equals to the upthrust or the apparent loss in weight, that simply means that upthrust, which is W air minus W water, will be equal to the weight of the fluid displaced. In this case, the fluid being displaced is actually the water being displaced. So this observation is what we call the Archimedes principle, that the upthrust will always be equal to the weight of the fluid displaced. Next. When an object is immersed in a fluid, it experiences an upward force due to that particular fluid. Remember, a fluid can either be a liquid or a gas. So this force is called upthrust. So upthrust is simply an upward force that is exerted on a body that is immersed in a fluid. And remember, upthrust force makes the body to appear lighter than it really is. From our previous experiment, whereby we were verifying the Archimedes principle, we stated that upthrust force will be equal to the weight of the fluid that is displaced. Therefore, in terms of statements, Archimedes principle can be stated as: when a body is partially or totally immersed in a fluid, it experiences an upthrust equal to the weight of the fluid displaced. So remember, the body can either be totally immersed in that particular fluid, or it can be partially. Partially simply means that the body is immersed in the fluid, but it is not totally. That is, it is halfway immersed in that particular fluid, such that some part of that particular body are outside the fluid, while some part of the same body are within that particular fluid. Therefore, we saw from a previous experiment that W air minus W fluid, which is simply the upthrust, will be equal to W beaker plus displaced fluid. In that case, we were using water, minus W beaker, which is simply the weight of the fluid displaced. In that case, we are talking of the weight of the water displaced. Therefore, from the Archimedes principle, we can say that upthrust is equal to weight of the fluid displaced, which is also equal to apparent loss in weight. But because weight is given by mass times gravity, it simply means that the weight of the fluid displaced can be given by the mass of the fluid displaced times the gravity. And therefore, the weight of the fluid displaced can also be given by, because we know that mass is equals to density times volume, it simply means that this formula can disintegrate into the density of the fluid displaced times the volume of the fluid displaced multiplied by the value of gravity. So this relationship shows us the factors that determine the magnitude of the upthrust or the magnitude of the weight of the fluid displaced. Therefore, we can conclude that the magnitude or the size of the upthrust force depends on two factors. One of the factor is the volume V of the fluid displaced, so the volume V here, and of course the density rho of the fluid displaced, so the density rho here. So remember, we are not taking gravity as a factor because on Earth the value of gravity is constant, which is usually either 9.8 Newton per kilogram or 10 Newton per kilogram. Therefore, a factor is supposed to be something that is varying. Therefore, the density of the fluid displaced and the volume of the fluid displaced are the two factors affecting the magnitude of the upthrust force. Then remember, we are talking of a fluid. We said that a fluid can either be a liquid or a gas. Therefore, upthrust in gases, again, if you want to find, suppose a body is floating in a certain gas. For example, this is a balloon which is filled with air. Then of course it is also floating in air, which is also a gas. So in this particular case, for that particular balloon to rise up or for it to float in the air, then in that case the upthrust must be greater than the total weight of that particular balloon plus its content. Like for this particular case, the weight of the air inside the balloon plus the fabric that is making up this particular balloon is greater than the weight W is greater than the upthrust force. So upthrust will simply be equal to the weight of the air that will be displaced. So whenever the total downward forces, that is the weight, is greater than the upward forces, which is the upthrust, then in that case the balloon remains at rest, or if there was some distance towards the ground, the balloon will actually move downwards. But whenever the weight of the balloon plus its content is equal to the upthrust force, then we expect the balloon to remain in a state of rest. However, if we fill the balloon with a gas that has very low density, for example, hydrogen gas, which has a low density of 0.9 kilogram per cubic meter, or helium gas, which has a low density of 0.18 kilogram per cubic meter. So if you compare these densities to the density of air, which is very great, of 1.3 kilogram per cubic meter, you see that hydrogen will always have a low weight as compared to the same volume of air. So that means if we fill the balloon with hydrogen or helium, that is a gas that has low density, that simply means that the air that will be displaced outside, which is equal to the upthrust force, because we are saying that upthrust is equal to weight of the fluid displaced, and in this case the fluid displaced here is air, because the air that will be displaced outside is denser and therefore its weight will be greater than the weight of the hydrogen plus the fabric in that particular balloon. It simply means that the upthrust force, which is equal to the weight of the air displaced, will be greater as compared to the weight of the hydrogen in that particular balloon plus the weight of the fabric that is making up that particular balloon. So whenever upthrust is greater than the weight of the, that is the upthrust, which is equal to the weight of the fluid displaced, whenever it is greater than the weight, the total downward forces, that is the weight of the hydrogen or the helium in that particular balloon, then in that case the balloon, the motion of the balloon will be upward, or the balloon will float in air. So the balloon can only rise upward whenever the upthrust is greater than the weight of the content in that particular balloon plus the fabric of that particular balloon. Next, we look at an example which reads that a solid sphere of radius 3 centimeters and made of a material of density 2.6 grams per cubic centimeter is fully immersed in a liquid of density 0.8 gram per cubic centimeter. We are required to determine the apparent weight of the solid sphere. Now remember, apparent weight will just be the difference between the total downward forces and the total upward forces. So total downward forces, we mean all the forces that are acting downwards, and the total upward forces, we mean the upthrust, or the total forces that are acting in the upward direction. Therefore, let's start by finding the total downward forces, of course, which is equal to the weight of the sphere. Remember, the weight will always act downward, and the only upward force will just be the upthrust force. So the total downward force is equal to weight of the solid sphere, which is equal to, remember, weight is equal to mass times gravity, and mass is density times volume. Therefore, the weight of the solid sphere can be given by rho Vg, that is density of the solid times volume of the solid multiplied by gravity. So we are given the density of that particular solid. We are told that the solid has a density of 2.6 grams per cubic centimeter. We convert into SI units. So remember that um, 1,000 kilogram per cubic meter is equals to 1 gram per cubic centimeter. What about 2.6 gram per cubic centimeter? It will just be over 1 gram per cubic centimeter multiplied by 1,000 kilogram per cubic meter, which will give us density of the solid as 2,600 kilogram per cubic meter. Therefore, the density of the solid we are given as 2,600 kilogram per cubic meter. Then the volume of the solid, we are told that it is a spherical solid, a solid sphere. The volume of a sphere is 4 over 3 pi r cubed. Then we are told that the radius of the sphere is 3 centimeters in SI unit. 3 centimeters over 100 centimeters times 1 meter, you'll obtain 0.03 meters. Therefore, the volume of the sphere will just be 4 over 3 times pi 3.142 times the radius of the sphere is 0.03. Then, of course, it is cubic. Then we multiply by the value of gravity, which is always 10. So if you take 2,600 times 4 over 3 times 3.142 times 0.03 cubic times 10, you'll obtain 2.940912 Newton. So this is an exact answer. Then we also need to find the upward forces. Remember the difference between downward and upward forces. That is what will give us the apparent weight of the solid that they want us to find. Therefore, the upward forces is only the upthrust force, of course, which is equals to the weight of the liquid displaced or the weight of the fluid displaced, courtesy of the Archimedes principle. So the weight of the fluid displaced or the liquid, in this case, it is the liquid that is being displaced in this particular case. So it will just be rho Vg. So density of the liquid displaced times volume of the solid or the volume of the liquid displaced times the gravity. So remember, this particular solid, because it is totally immersed in that particular liquid, its volume will be equal to the volume of the liquid that will be displaced from this particular container. Because remember, volume is the amount of space occupied by a body. Therefore, the amount of space that this particular solid will occupy will be equal to the amount of space or the amount of water or the liquid that will be displaced from this particular container. That is why you are saying that the volume of the liquid displaced will just be equal to the volume of that particular solid because it is totally immersed. Therefore, the water that or the liquid that it displaces will be equal to the volume of the liquid that it displaces will be equal to the volume of that particular solid sphere. Then, of course, multiplied by gravity. So density of the liquid displaced, we are given as 0.8 gram per cubic centimeter into SI unit. You simply multiply it by 1,000 because we know that 1,000 kilogram per cubic meter is equal to 1 gram per cubic centimeter. What about 0.8 gram per cubic centimeter? So that will be over 1 gram per cubic centimeter times 1,000 kilogram per cubic meter, which gives us 800 kilogram per cubic meter. Therefore, the density of the liquid displaced is 800 multiplied by the volume of the solid, which is equal to the volume of the liquid displaced, will just be the volume of that particular solid, which of course the solid was spherical in nature, so it will be equal to the volume of the sphere, which is 4 over 3 pi r cubed. So 4 over 3 pi is 3.142 times the radius was of course 0.03 cubic meter, then times gravity, which is 10. So if you take 800 times 4 over 3 times 3.142 times 0.03 cubic times 10, you will obtain 0.904896 Newton. Therefore, the apparent weight of the solid is just the difference between the downward forces and the upward forces. So downward forces, we found it as 2.940912 Newton, then minus upward forces, which is just the upthrust, will be 0.904896 Newton. So this difference will give us 2.036016 Newton, of which correct to 4 significant figures can be 2.036 Newton. So that is the apparent weight of that particular solid. So the key thing in these particular questions is simply to find the total upward force and the total downward forces. Then from there, the difference between the two will always give you the apparent weight of that particular solid or that particular body that is displacing that particular fluid. Lastly, I have an exercise that I recommend you should try at your own free time to get the understanding of the concept that you have just learned. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in. And as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that kindness is a language which the deaf can hear, the blind can see, and the dumb can speak. So the quote is encouraging us to be kind to everyone we meet in life, because sometimes it takes just one act of kindness to change someone else's life. Recall that no act of kindness, no matter how small it might seem to be to you, is ever a waste of time, because nature has its own way of rewarding you back through the law of karma. And lastly, remember to be a rainbow in someone else's storm. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Thank you for the continued support. Thank you for the positive comments. I really appreciate, and I don't take that for granted. Until next time, this is Kind Tuition Academy. Thank you very much.